In a previous video, we looked at using Ka values to quantitatively compare the strengths of different acids. In this video, we're going to look at a qualitative treatment of acid and base strength by looking at how the structures of the molecules can help us to predict the relative strengths of acids. So, in general, the stronger an acid is, the more stable its conjugate base is going to be. And so when an acid loses a proton, it forms a conjugate base, which has an extra lone pair of electrons that results from the loss of that H+. And so to determine the stability of a conjugate base, we're going to look at how stable is that lone pair that we create by losing the H+. And the more stable the conjugate base is, the stronger the initial acid is going to be. So there are a number of factors that we can look at that influences the stability of this lone charge that we create when we lose that H+. And those four main factors are the type of atom that the lone pair and the charge ends up on, whether or not that lone pair is going to be resonance stabilized, whether induction can help stabilize it, and then also what type of orbital that lone pair resides in. So one way to remember these different factors is with this acronym REO, atom type, resonance, induction, orbital. So let's take a look at each one of these factors individually. So the most important thing that we look at is what type of atom is going to end up with that charge and that lone pair. So if I want to compare the acidity of butane and propanol, I want to look at the conjugate bases, right? So what happens when I lose these H pluses? So in both cases, I end up with a negative charge. In the case of butane, I end up with a lone pair on a carbon atom. And in the case of propanol, I end up with a lone pair on an oxygen atom. And so the two things that we look at in terms of the type of atom is the larger the atom is, the more stable the negative charge will be. Now, because carbon and oxygen are in the same row of the periodic table, they're about the same size. So the next thing that we look at in terms of atom type is electronegativity. So the more electronegative atom will better stabilize the negative charge. So because oxygen is more electronegative than carbon, the conjugate base of propanol is more stable than the conjugate base of butane. And then, so as we said before, right, the more stable the conjugate base is, the stronger the acid that led to that conjugate base will be. So because this conjugate base is more stable, propanol is the stronger acid. All right, one more example. So if I wanted to predict whether this compound or this compound was the stronger acid, I need to look at the conjugate bases. And so these compounds are very similar. In this case, the negative charge ends up on, and lone pair ends up on a sulfur. In this case, the negative charge and lone pair ends up on an oxygen. Now, sulfur is in the third row, oxygen is in the second row, and so we said on the previous slide, right, that size is the most important thing. So sulfur being significantly larger, being in the third row than oxygen, makes this conjugate base more stable, and so this is going to be the stronger acid. All right, the second factor that we look at is resonance. If we can spread out that lone pair and negative charge through resonance, that's going to stabilize it. And so if I compare ethanol with acetic acid, right, I want to look at the conjugate base that we form again. Right? So in the case of ethanol, right, that negative charge and lone pair is localized on that oxygen. In the case of acetic acid, I can make this alternate resonance structure, and so I can spread that negative charge between those two oxygen atoms. So the fact that I can spread out or delocalize that lone pair negative charge means the conjugate base from the acetic acid is more stable than the conjugate base from the ethanol, and so acetic acid is more acidic than ethanol. All right, so induction, right, this is where we have electronegative atoms or electron withdrawing groups, right? And so they can essentially withdraw electron density from the negative charge and lone pair that we form, thereby stabilizing it, right? Because we're kind of spraying it out again. So when we look at acetic acid versus trichloroacetic acid, all right, they're both going to have the resonance structures where we can spread out the negative charge between those two oxygen atoms, but the presence of the electron withdrawing groups in the trichloroacetic acid is going to further stabilize that negative charge and lone pair that we create by removing that H+. So the trichloroacetic acid is going to be more acidic. Right? And so in general, the more electron withdrawing groups, the more stable the conjugate base is going to be, and the closer the electron withdrawing group is to the negative charge, the more stable the conjugate base is going to be. This is just another example. Right? We know that lower pKa values mean stronger acids. Right? So we can see as we go from having none to 1 to 2 to 3 chlorine atoms, right, the pKa goes down, indicating that the acid strength increases as we move from left to right along that series. All right, the final factor that we look at is the orbital type. So the closer electrons are held to the nucleus, the more stable they are. So the smaller the radial extent of the orbital that the lone pair finds itself in, the more stable that negative charge is going to be. And in general, as we go from sp3 to sp2 to sp orbitals, the electrons are held closer to the nucleus. So a lone pair and negative charge in an sp orbital is going to be more stable than a lone pair and negative charge in an sp3 orbital. So if we consider these two hydrogen atoms and we wanted to know which one is more acidic, right, we end up with either this conjugate base or this conjugate base. Right? In this case, right, the lone pair is on an sp2 hybridized carbon. In this case, the lone pair is on an sp hybridized carbon. So the sps, the electrons are held closer to the nucleus, so this is going to be more stable. So this hydrogen is going to be more acidic. All right, and then just one more example here. Right, when we look at the series ethane, ethylene, and acetylene going from sp3 to sp2 to sp, we can see the decrease in the pKa value, indicating the increase in acidity as we go from sp3 hybrid orbitals to sp2 to sp. So in general, the order that we considered these factors is their order of importance. So generally, the type of atom is the most important, then resonance, then induction, and then the final thing we would look at, if all of the things are equal, would be the orbital where the charge resides. Now, this is useful in that it usually works, but it's not 100%. And so there will be some cases where we might have to use pKa's to determine the relative acidities because this ordering breaks down. But it works a lot of the time. Here's just one example. If we were to compare the acidity of ethanol versus propylene, if we consider the atom type, right, having the negative charge on an oxygen versus having the negative charge on the carbon, we would predict that ethanol is the more acidic. Now, propylene's conjugate base is resonance stabilized, right? I can move the lone pair here to a double bond, and then move this double bond to make a lone pair here, and so that should lead to stabilization, but the atom type comes before resonance, and so we would expect that the atom type wins out, and in fact it does. The pKa of ethanol is significantly less than the pKa of propylene. But this won't always be the case. Here's one other example. So in this case, we know the equilibrium lies to the right because we know the pKa values, but if we were just predicting which conjugate base is more stable, either the NH2 or the lone pair here on the acetylene, right, we would have predicted due to atom type that the it should be the nitrogen conjugate base should be more stable than having the lone pair on here, right? But that's not the case. right? The equilibrium lies to the right, indicating that this is the more stable conjugate base, and so this goes against our predictions. And so for this, we would have needed to just use the pKa's. Now, if I don't give you the pKa's and I ask you to predict, which is the stronger acid, then using the ARIO sequence is always going to work for those examples. If it doesn't work, we'll have to give you the pKa's. All right, so we've looked at a couple examples. And so in these cases, I'm not giving you the pKa's, so we know that the ARIO ordering of importance is going to work. So if we want to know whether this hydrogen or this hydrogen is more acidic, right, we need to look at the conjugate bases, right? So essentially we either have the negative charge on this oxygen or on this oxygen, right? These things are fairly similar, right? We're going to be able to draw resonance structures where the negative charge is on either this oxygen or this oxygen, right? The difference being, right, the presence of this fluorine, right? So the atom type is equivalent, the resonance is equivalent, so when we go to induction, right, the presence of the fluorine, an electronegative atom, an electron withdrawing group, is going to stabilize this conjugate base relative to this one. So the red proton is going to be more acidic than the blue one in this case. All right, here's one more example. So we have these two protons, and we want to know which one is more acidic. So if we consider the red one first, we would get this conjugate base, right? And then I can draw two different resonance structures. One where the lone pair moves down to a double bond here, then the lone pair moves up, and the negative charge is on the oxygen, and then essentially going the other way, right, where I can put the negative charge here, right? So in this case, I've got the negative charge spread out between two oxygens and a carbon. When I look at taking away this proton, I can only draw one resonance structure, right? And so I can only get the negative charge between this carbon and this oxygen. So the fact that I can spread out the negative charge more with resonance in the red case, right, that indicates that the red proton in this case is again going to be the more acidic. So the red one is more resonance stabilized than the blue one. The blue one is resonance stabilized, but not as much as the red one. All right, final example. So again, I'm comparing the red to the blue. And in this case, right, if I look at the conjugate base, when I take the red off, I'm going to be able to, by resonance, spread out that negative charge between the two oxygen atoms. In this case, if I remove one of the blue hydrogens, I'll be able to spread out the negative charge between these two nitrogens, right? And so if we look at A, right, atom type, right, I'd rather have the electrons spread out and the negative charge on the oxygens than the nitrogens. So again, the red is going to be the more acidic.